On March 11, 2011, the ocean rose like a monster. A wall of water nearly 50 feet high, traveling at the speed of a jet aircraft, crashed into Japan's coastline. In minutes, an entire civilization was underwater. More than 20,000 people lost their lives that day. Over 120,000 homes were completely destroyed. Entire towns were erased from the map as if they had never existed. Japan was brought to its knees. The Fukushima nuclear power plant suffered a catastrophic meltdown. Radiation spread across the region, forcing hundreds of thousands to evacuate. The economic damage exceeded $235 billion, making it the most expensive natural disaster in recorded history. The old sea walls that were supposed to protect these communities had been designed for waves up to 26 feet. The tsunami that hit was nearly double that height. The walls crumbled like sandcastles. Japan's coastal defense had completely and catastrophically failed. And in that moment of unimaginable grief, Japan made a decision that would stun the entire world. They would build a wall, not just any wall, a concrete Great Wall stretching nearly 400 kilometers along the entire northeastern coastline. A wall towering nearly 50 feet above sea level, with foundations plunging 80 feet deep into the earth. Designed to absorb the impact of millions of tons of raging ocean water. The budget was staggering, over 12 billion United States dollars. More than 30,000 engineers, workers, and geotechnical specialists would be mobilized. Thousands of heavy-duty machines would operate non-stop for years. Japan was about to undertake the largest coastal defense construction project in the history of human civilization. But before a single shovel hit the ground, Japan needed to answer a terrifying question. How tall should this wall actually be? How thick? What angle? What shape? Get any of these wrong, and the next tsunami would destroy it again. The answer would come from one of the most advanced tsunami research programs ever conducted. Engineers collected every piece of data from the 2011 disaster: wave heights, impact forces, water velocities, flooding patterns, structural failure points of every old wall. Then they recreated the tsunamis. Inside enormous laboratory wave tanks, engineers built scaled-down models of the coastline and generated artificial waves that perfectly mimicked the 2011 disaster. They watched how water hit, overtopped, and destroyed different wall designs. After hundreds of tests, they kept adjusting, making the wall taller, making it thicker, changing the slope angle, deepening the foundations. Each modification was tested again and again until the models showed the absolute best possible performance against maximum force waves. The final design was locked in. A wall standing 14 to 15 meters above sea level, foundations driven 20 to 25 meters deep into the ground, a wide trapezoid-shaped base for maximum stability, and a reinforced steel core throughout. With the design finalized, engineers now had to determine exactly where this massive wall would stand. The route stretches along the Tohoku coastline in northeastern Japan, through 4 prefectures: Aomori, Iwate, Miyagi, and Fukushima, the region that absorbed the full tsunami impact. This would become the longest and most unified coastal defense line in Japan's entire history. nearly 400 kilometers of continuous protection, longer than the distance from New York to Washington, D.C., a concrete barrier between civilization and the ocean's fury. Before construction could begin, the entire coastline had to be cleared. Crews demolished old, damaged houses, removed destroyed infrastructure, pulled out broken power lines and ruptured pipelines. The remnants of the 2011 disaster had to be completely erased first. Simultaneously, engineers built the support infrastructure needed for construction. New access roads were carved along the coast. Material storage yards were established every few kilometers. Crane platforms, concrete mixing stations, and temporary drainage systems were installed to ensure year-round construction. Much of the Tohoku coastline sits on weak, sandy soil. Building a 50-foot wall on unstable ground would be like placing a skyscraper on quicksand. The wall would crack, sink, and eventually collapse. The ground itself had to be completely transformed first. Engineers drilled detailed geological surveys along the entire route. They mapped every layer of sand, clay, and rock beneath the surface. Then the ground reinforcement began. Deep concrete and steel piles were driven into the earth, reaching stable geological layers below. Layers of crushed stone were spread and compacted. Sand was stabilized with chemical binding agents. The surface was pressed and rolled until it became dense enough to support the enormous weight that would sit on top. A solid foundation created from weakness. With the ground stabilized, massive excavators began digging the foundation pits. In some sections, these pits went more than 20 meters deep. Near the shoreline, where seawater constantly threatened to flood the excavations, crews faced an entirely different engineering challenge. To keep the ocean out, workers built temporary retaining walls called cofferdams around each excavation site. These watertight barriers held back the sea, allowing crews to work in dry conditions even though they were digging just meters from the Pacific Ocean itself. Once the pits were dry, a massive base layer of concrete was poured into each foundation. Then came the steel. Dense reinforcement cages made of thick rebar were assembled inside the foundation, creating an incredibly strong skeleton that would anchor the wall to the earth. These foundation blocks were engineered to be extremely heavy and wide. The trapezoid shape distributed the wall's weight across a broad area, preventing it from being pushed over or sliding backward when millions of tons of tsunami water slammed into it. Above the foundations, the wall itself began to rise. Workers assembled tall, thick cages of steel reinforcement bar, precisely following the laboratory-optimized design. Every bar was positioned to exact specifications. Every connection was welded and inspected. There was zero tolerance for error. Wooden and steel formwork panels were then set in place around the rebar cages, creating molds for the concrete pour. These forms had to be perfectly aligned because any deviation would create weak points that a tsunami could exploit and shatter apart. Concrete was then pumped into the formwork section by section. Each block, usually several dozen meters long, was carefully poured using specialized high-pressure concrete pumps. Vibrators were inserted into the wet concrete to remove air bubbles that could weaken the structure. Each section was then left to cure under carefully controlled conditions. Temperature and humidity were monitored constantly. Too much heat would cause cracking. Too little moisture would weaken the bond. Only after passing rigorous inspection was the next section connected. Block by block, section by section, the wall grew along the coastline. Hundreds of construction sites operated simultaneously across all 4 prefectures. From above, it looked like an army building a fortress against the sea, a concrete ribbon taking shape. But the wall alone was not enough to stop a tsunami. When a wave hits a flat concrete surface, the impact force is concentrated at one point. That concentrated energy can crack even the strongest wall. Japan needed something to break the wave first. The solution was brilliant. On the ocean-facing side of the wall, crews installed thousands of specially designed concrete units called tetrapods. These four-legged structures look almost alien, but their geometry is engineered to break apart wave energy before it reaches the wall. Alongside tetrapods, engineers also placed Dolos blocks. These interlocking concrete shapes were stacked in multiple layers around the wall's base, creating a massive energy absorption zone. By the time any wave reached the actual wall, its destructive force was already significantly reduced. Some sections of the wall featured stepped faces on the ocean side. These staircase-like surfaces forced incoming water to climb upward in stages, dissipating energy at each step. Other sections used sloped surfaces and splash reduction ledges to redirect water upward and backward. On the landward side of the wall, the engineering continued. Soil and crushed rock were packed against the back surface, providing additional structural support. Drainage channels were built to prevent rainwater from pooling behind the wall, which could weaken its foundation over time. In several sections where extra impact resistance was needed, crews added an additional layer of precast concrete armor panels onto the outer wall surface. These interlocking tiles were lifted into place by crane and arranged in tight, uniform patterns for maximum strength. Once secured, these armor tiles created a reinforced outer shell designed to withstand decades of relentless pounding from the Pacific Ocean waves. The wall was not just built to survive one tsunami. It was built to endure generations of oceanic punishment without failing. Many sections of the wall include walkways and inspection roads built directly on top. These allow maintenance crews to access every part of the structure for regular inspection. In some towns, the seawall even doubles as part of the local road network. Safety railings and fences were installed along the top edge. Emergency access ladders were placed at regular intervals. Warning signage in multiple languages was posted throughout. Every detail was designed with one purpose: saving human lives when the next tsunami arrives. But Japan's coastline is not just beaches and residential areas. Busy fishing ports and commercial harbors dot the entire Tohoku region. Ships need to enter and exit these ports daily. A solid wall with no openings would destroy the local economy. Japanese engineers solved this with one of the most ingenious systems ever designed: tsunami gates. In some ports, they built top-down gates. A massive steel panel hangs suspended between two concrete towers high above the harbor entrance during normal operations. Ships pass freely underneath during normal conditions. But the moment a tsunami warning is issued, hydraulic motors activate and the massive steel panel drops down from above. Within minutes, the entire harbor entrance is sealed shut like a vertical fortress gate. In other harbors where overhead towers were not practical, Japan designed bottom-up rising gates. These gates normally lie completely flat on the seafloor, invisible and unobstructive. Ships sailed directly over them without even knowing the gates exist beneath the water. When a tsunami approaches, a powerful hydraulic system activates from below. The entire gate rises upward from the seafloor, locking into the concrete sidewalls to form a solid, impenetrable barrier. The ocean that was welcome moments ago is now completely blocked out. Because these gates sit permanently underwater, they must be built with highly corrosion-resistant steel alloys. Every hinge is fully sealed against seawater and sand intrusion. Regular underwater maintenance teams inspect these gates to ensure they will function perfectly when disaster strikes. Although the wall follows one unified design across 400 kilometers, every section required minor adjustments. Local terrain varied, soil conditions changed, coastal depths differed. Engineers adapted each section individually while maintaining the overall structural integrity and protective capability of the entire system. The construction stretched across 5 to 7 years of continuous non-stop work. Thousands of machines operated around the clock. Concrete trucks made hundreds of thousands of trips. Cranes lifted millions of tons of steel and precast concrete into position along the coastline. Workers endured brutal conditions. Coastal winds whipped across construction sites. Rain and storms halted progress repeatedly. Summer heat and winter cold tested every crew member's endurance. Yet they pushed forward, driven by the memory of 20,000 lives lost. After years of relentless effort, the wall was finally complete. Nearly 400 kilometers of reinforced concrete barrier standing guard along the entire Tohoku coastline. From above, it looked like a concrete Great Wall separating Japan from the Pacific Ocean. But building the wall was half the battle. Japan also completely upgraded its tsunami early warning system. Hundreds of seismic sensors and ocean pressure detectors were deployed across the Pacific seafloor. These sensors can detect earthquake-generated waves within seconds of formation. The moment a potential tsunami is detected, alerts are broadcast simultaneously through television, radio, mobile phones, and loudspeaker systems across every communally recognized evacuation route. Every second of warning saves lives. And that's exactly what the wall is designed to provide: time. Simulations showed that the new seawall system could reduce tsunami impact forces by 30 to 50%. More importantly, it provides several extra life-saving minutes for complete coastal evacuation. Those extra minutes could save tens of thousands of lives during a major tsunami event. In 2011, many victims died not because they didn't know a tsunami was coming, but because they did not have enough time to reach higher ground. Coastal roads and fishing ports that were completely wiped out in 2011 are now protected behind the wall. Residential areas have been rebuilt with confidence. Schools and hospitals, once destroyed, now stand safely on the landward side of the barrier. But not everyone celebrates this wall. Many residents say it has stolen their ocean view. Fishing communities complain they can no longer see the sea that has been their livelihood for generations. Some call it an ugly concrete prison along the coast. Critics also raise a deeper concern. They argue the wall creates a false sense of security, that people living behind it might believe they are completely safe and delay evacuation when a real tsunami warning comes. Complacency could become more dangerous than the wave itself. And there is the fundamental question that no engineer can fully answer. Can any wall truly stop a mega tsunami? The 2011 wave was nearly 50 feet high. What if the next one is 60 feet or 70? Nature has no upper limit. Japan's engineers acknowledge this reality openly. They admit the wall cannot stop every possible tsunami, but they maintain it was never designed to be an absolute barrier. It was designed to be a time machine, a structure that buys precious evacuation minutes. Combined with upgraded early warning systems, improved evacuation routes, reinforced buildings, and continuous public education, the wall is just one layer in a comprehensive defense strategy. Japan calls it disaster mitigation. reducing the damage when you cannot eliminate the threat entirely. Today, the nearly 400-kilometer tsunami wall stands as a monument to human resilience. It is not perfect, it is not invisible, it is not universally loved, but it represents something profound, a nation's refusal to accept the same tragedy twice. Japan looked at the ocean that took 20,000 of its people and said, "Never again." And then it built a wall that the entire world cannot ignore. Not because it is perfect, but because it proves that courage can be poured in concrete. What do you think about Japan's tsunami wall? Is it enough to protect against the next great wave? Or does nature always find a way? Share your thoughts in the comments below. Subscribe and turn on notifications for more incredible engineering stories.